Okay, on to our next biomolecule, our final biomolecule, major biomolecule. We're going to talk about lipids. Lipids. As you know, lipids are fats. You can probably tell that by some of these images. You see a lot of butter here. You see some delicious looking olive oil or vegetable oil, something over there. Also, probably most importantly, because we could not exist without this phospholipid bilayer, lipids exist in the cell membranes of all living organisms. Very, very important, which we will talk about all three of these. So let's go ahead and continue here. Lipids, as you know, are composed of carbon, hydrogen, and oxygen. However, they're in much different quantities than you're going to find them in, as we did in carbohydrates, right? If you remember, carbohydrates had twice the amount of hydrogen as they had carbon, and they had about equal amounts of carbon and oxygen. Lipids have very little oxygen. A little note here. Very little. Very little oxygen. Not very much. They're mainly long hydrocarbon chains, mostly carbon and hydrogen. There are different groups of lipids. One of these groups being kind of your typical fats or triglycerides, in which you have these long chains, if you'll notice, of carbon and hydrogen connected to this glycerol molecule here. The glycerol. And these are fatty acid chains here. Fatty acid chains. There we go. Phospholipids. Phospholipids had these two fatty acid chains as well. They also have this glycerol molecule in the middle, but on the other side, they have this kind of hydrophilic area with a phosphate group in it. Hydrophilic region. You should remember the hydrophilic means water-loving. Of course, fats themselves, these fatty acid chains, are hydrophobic. We will revisit this again. Visit this again in this video, so don't worry about it. Steroids are these four-ring fused carbon structures in which they vary outside of these rings or which attach to these rings, which creates different molecules. This is typically used in signaling and cell membrane structure. Again, we'll talk about those in a little bit, but those are steroids. It's important to note that lipids do not form polymers, at least not in the same way that other biomolecules do. If we talked about carbs, we had starches, which were long chains of carbohydrates, right? We had proteins, which formed long strings of amino acids, right? Nucleic acids, they formed long strings. Your DNA is a long string of bases, right? So these form long, complex strings. These do not. Lipids do not form these long, complex molecules. They kind of group in threes or twos here, as you see in the phospholipids, or in these kind of monomer steroid forms here. You're not going to see these chained together the way you do all of the other biomolecules. So they're kind of unique in that. They are big molecules. They're made of smaller subunits. That's true, like this fatty acid chain and glycerol combination. But it is not a continuing chain. This won't continue on and on and on and on, like you'll find in other biomolecules. Okay, so again, long hydrocarbon chains. Are they polar or nonpolar? Are they hydrophilic or hydrophobic in general when you look at these lipids? So go ahead and pause the video and tell me what you think, polar or nonpolar, hydrophilic or hydrophobic. Okay, you should have noted that lipids are nonpolar molecules. They are also typically hydrophobic. The reason they are nonpolar and hydrophobic is because the majority of this molecule is carbon and hydrogen. Carbon and hydrogen. Because there's so much carbon and hydrogen in this molecule, it makes it nonpolar. Typically, in polar regions, you'll find a lot of oxygen, a lot of nitrogen, things like that. Those highly electronegative atoms. You don't find many of those here. Sure, you've got some oxygens on the end over here, a couple of oxygens, but in the end, it's capped off with a bunch of carbon. And there's not a polar region to this molecule, not in any real sense. Basically, because of that charge gets distributed across these long chains, long hydrocarbon chains. Okay, so lipids function in long-term energy storage. All carbon and hydrogen. Again, these carbon-hydrogen bonds here, and you may not realize this, but all of these carbon to carbon. I'm sorry, I said carbon-hydrogen. These carbon-to-carbon bonds right here, they store energy. Right? So this is where that energy comes from. It's from these regions here, these carbon-to-carbon bonds. Carbon-to-carbon bonds are a lot of energy. So lipids store a lot of this energy for us, right? They have a lot more carbon-hydrogen bonds than carbohydrates do. Just judging by the amount of big oxygen molecules and stuff you'll find in carbohydrates compared to lipids, which have Again, a lot more carbon and hydrogen, right? This helps to cushion organs as well. Also insulates the body. Insulates the body, so you can think of it a lot. You have a lot of fat inside of your tissues that helps to cushion your heart, lungs, everything that's inside of you, so it's not bouncing around. It also acts as insulation, particularly in things like whales. Whale blubber is a lot of fat in whale blubber. Um, so these are some examples of fat insulating or cushioning. Tricycglycerol. These are three fatty acids linked to a glycerol. This is typically how you're going to see, triglycerides represented. The important thing to note from this is this line right here: ester linkage. We need to know the bonds that form between each of these, right? So for nucleic acids, we had something called, and you can go ahead and pause to remember this if you want to try and remember it. For nucleic acids, I'm just going to put Na, nucleic acids. You have phosphodiester. Phosphodiester bonds, right? For proteins, what did you have for those? Go ahead and pause it. Come back. Ready. We have peptide bonds. Peptide bonds. Okay, let's pause and let's talk about carbs. What kind of bonds did you have between carbs? Okay, you should have said glycosidic linkages. And what about between, linking to this glycerol, this gray molecule here, this glycerol molecule? Glycerol. So how do these things link to this glycerol molecule? Well, that's called an ester linkage, that is the bond between these fatty acid chains and a glycerol molecule. Again, it's between the OH. Do you remember what the name of that functional group is? Hydroxyl and a COOH. Do you remember what this functional group is? This is a carboxyl. Okay, saturated fats versus unsaturated fats. Saturated fats, I like to think of this as meaning saturated with hydrogen. Saturated with hydrogen. Unsaturated fats are not saturated with hydrogen, as we'll see in a bit. There are no double bonds, no carbon-to-carbon double bonds in saturated fats. These are long, straight chains. If I was to draw a line diagram of some of these fats, they would look like this. Right? There are double bonds in unsaturated fats. So you're going to see, in these ones, you're going to see some bonds that look possibly like this. Maybe they go off. Double bonding, right? So you'll see double bonds inside these unsaturated fats. You're not going to see these in the saturated fats. These are long, straight chains. Most animal fats are saturated, things like butter. They are solid at room temperature. They also contribute to cardiovascular disease because of their ability to clump together and stack, right? These molecules stack very easily on one another. That's why they're solid at room temperature. That's why they're kind of worse for you, is because they stack very easily in your system. They're like Legos. They look something like this. You're going to see them very long, straight molecules. They have hydrogens everywhere. They have the maximum number of hydrogens because, again, they are saturated hydrogen. Carbon, the ones that have double bonds, you'll find these in plant and fish fats typically. Vegetable oils, these are usually liquid at room temperature. And the kinks made by double bonded C prevent the molecule from packing tightly. These kind of do not pack as neatly. These are like melted Legos, if you will, right? They don't pack together very neatly because these double bonds, these missing hydrogens, are creating kinks in this structure. So these are not saturated with hydrogen. You could get rid of double bonds and add hydrogens to an unsaturated fat, right? So please know the difference between saturated and unsaturated fats. Okay, phospholipids. Are they hydrophobic or hydrophilic? Tough question, but why don't you go ahead and answer this? Pause and try and answer this question to the best of your ability. Well, for the fatty acid tails, if you hopefully, obviously it has the answer right here, but you should have said something. You should have said the fatty acid tails are hydrophobic. Remember, these are fats, right? Almost all carbon and hydrogen, or they are all carbon and hydrogen as far as these tails are concerned. The phosphate head is hydrophilic, right? Phosphate head loves water, and this is how these phospholipids kind of arrange in our system. This is a very simplistic look at the phospholipid membrane down here. You'll notice you have this hydrophobic portion, just put phobic, and this philic portion on the outside and inside of the cell. Philic. Hydrophilic and hydrophobic, right? This is how cell membranes arrange. It's the most important feature of cell membranes. Um, Without this, no cellular life could exist. Without this phospholipid membrane and the ability of hydrophobic substances to dissolve well in each other and hydrophilic substances to dissolve well in each other. Remember, like dissolves like. Stuff that is like each other dissolves well in each other. So these hydrophilic portions will tend to face towards water. Hydrophobic portions will face away from water and towards each other. They just split personality. Okay, steroids. These are 4 fused carbon rings. Different steroids attach different functional groups to the rings and have different meaning. If you look at these, there's some differences between these 2 signaling molecules up here. These are signaling molecules that can move through the phospholipid bilayer to change things inside and cause different cascade reactions. When we talk about cell signaling a little bit later, we'll talk a little bit more about that. But there's some more differences down here. Very small differences, right? Can mean a big difference in what happens. These are typically used for signaling. Cholesterol is also used in the structure of the cell membrane. You can see these cholesterol molecules kind of arranged in here. They help to give this bilayer some fluidity, right? These cholesterol molecules help to give it some maintain flexibility and fluidity. Help to maintain the structure of this phospholipid bilayer. Again, this is an example of cholesterol. Sex hormones. Again, you'll probably notice down here there's some sex hormones, an estrogen down here and an androgen. One of these is testosterone, an estradiol. And these are your sex hormones. So, just some interesting note about some of the some lipids you might not have heard about in your freshman class. So, lipids overall. What we need to know about lipids: monomers, fatty acids, and glycerol. These can be considered monomers of lipids. Right, this is how they connect. Steroids only have a monomer form; they don't link together. Cholesterol as well. These do not polymerize into long chains. That's kind of important to note. Okay? Phospholipids make up our bilayer of our membrane, which we will talk about next unit in depth. Triglycerides, these are storage molecules, right, or fat storage molecules. Ester linkages, this is another important thing to know, is the name of the bonds that form between these. They're also formed, again, through dehydration synthesis. And our functions for fats: energy storage, insulation and cushioning, cell signaling, as in testosterone and estrogen, estradiol. There's some examples of that. Membrane structure, right? Phospholipids, and even those cholesterol molecules, right? So I'll put phospholipids and cholesterol molecules. So this is kind of the basic overview of what you need to know about lipids. I hope that helped, and I'm sorry this video is a bit longer than I meant for it to be, but that's the basics of lipids. All right.